Have you ever looked up at the night sky and felt a profound sense of awe, a whisper of questions about our existence echoing in the vast silence? We as humans are storytellers, and no story is more grand, more utterly captivating than the tale of our universe. We often tell it starting with the Big Bang, a moment of cataclysmic creation from nothing, a singular point where everything we know burst into being. But what if that's the wrong perspective? What if our universe wasn't a beginning, but an exit, the chaotic, fiery birth of our cosmos, the very fabric of space-time tearing itself open? Could be the other side of a black hole, from a universe that came before. This isn't just a philosophical musing. It's a journey into the deepest, most mind-bending corners of theoretical physics. To truly grasp this radical, almost unbelievable idea, we must first confront the familiar, the undisputed titans of cosmic mystery, black holes. You've heard of them, seen their mesmerizing images, those shadowy silhouettes against a swirling backdrop of incandescent gas, like the groundbreaking picture captured by the Event Horizon telescope. These are cosmic behemoths, born from the death throes of massive stars, collapsing under their own immense gravity. They are the universe's ultimate traps, cosmic points of no return. Once anything, light, matter, even the very fabric of space-time itself, crosses that invisible boundary we call the event horizon, it is irrevocably lost to our universe. It's a one-way street, a descent into an unknown, unfathomable abyss. The gravity within a black hole is so potent that it bends the very fabric of space-time into an infinite singularity, a point where our current laws of physics break down entirely. The idea of an object with gravity so strong that light cannot escape was first conceived by Pierre-Simon Laplace way back in 1795, using Newton's theory of gravity. Later, Albert Einstein's general theory of relativity, published in 1915, provided the mathematical framework that truly predicted these gravitational monsters. But here's where the story takes a truly mind-bending turn, where the familiar gives way to the utterly bizarre. What if, for every cosmic devourer, there existed a cosmic giver? What if, for every ultimate trap, there was an ultimate escape? Imagine, if you will, the exact opposite of a black hole. This is the aha moment that has captivated physicists for decades. The very same equations of Einstein's general relativity that predicted the black holes we have now observed also predict their perfect time-reversed twin. This isn't just science fiction. It's a profound mathematical ghost in the machine of physics. These theoretical objects are called white holes. If a black hole is a one-way street into the unknown, then a white hole is its mirror image, a one-way street out of the unknown. If nothing can escape a black hole, then, by this stunning reversal of logic, nothing can ever enter a white hole from the outside. Our classical understanding of black holes says that anything falling in collapses to an infinitely dense point called a singularity. But infinite density and zero volume are concepts that make quantum physicists deeply uncomfortable. They suggest that at these unimaginably small scales, quantum gravity effects would prevent such an infinite collapse. Instead, when matter reaches the extreme densities at the heart of a black hole, it doesn't reach an infinite singularity, but undergoes a quantum bounce. This quantum bounce offers a tantalizing solution to one of physics' most profound puzzles, Stephen Hawking's black hole information paradox. For decades, physicists have grappled with the question of what happens to the information of everything that falls into a black hole. If it's truly destroyed at the singularity, it violates a fundamental principle of quantum mechanics. That information can never be truly lost, only transformed. But if a black hole eventually transitions into a white hole, then that information, albeit scrambled and utterly transformed, could theoretically be released back into the universe. The story of a cosmic great escape can be explored, reframing the black hole information paradox not as a problem of loss, but as a journey of transformation, where information is not destroyed, but re-emerges through a white hole. And this brings us back to that initial, breathtaking provocation. If white holes are cosmic fountains of matter and energy, constantly erupting into existence, could one of these primordial white holes be something far grander, far more intimate than we ever imagined? What if the universe's most secret back door isn't just a theoretical curiosity, but the very origin point of our own existence? While white holes remain a frontier of theoretical physics, existing on the bleeding edge of our understanding, they represent a profound possibility. They force us to question everything we thought we knew about beginnings and endings, about creation and destruction. Perhaps the Big Bang wasn't a beginning at all, but rather a grand escape, the universe's secret back door, opening to reveal everything we call home. The universe, my friends, is a place of endless mirrors, of profound symmetries that often elude our everyday intuition. We just explored the dizzying thought that our own Big Bang wasn't a beginning at all, but perhaps a grand escape, the universe's secret back door opening to reveal everything we call home. It's a concept that flips our cosmic narrative on its head, suggesting creation isn't always from nothing, but sometimes an exit. This mind-bending idea, this notion of a back door, brings us face to face with one of the most mysterious and profound theoretical objects in all of physics, the white hole. For most of us, the universe's ultimate devourers, black holes, are a familiar terror. We've seen the stunning images from the Event Horizon Telescope, glimpsed the fiery halos of supermassive behemoths like TIM-87 Cygni and Sagittarius A, understood their inescapable gravity, their ravenous hunger. But what if I told you that for every black hole on the cosmic map, there's a theoretical counterpart, a perfectly symmetrical opposite, that has been hiding in plain sight within the very equations that describe black holes themselves? Imagine the heart of a black hole, a place so dense, so extreme, that our most cherished laws of physics simply break down. This is the singularity, a theoretical point of infinite density and zero volume, born from the collapse of a massive star. For decades, it has been the ultimate cosmic brick wall, a place where general relativity, Einstein's magnificent theory describing gravity and the large-scale structure of the universe, throws up its hands in despair. It's like trying to divide by zero in the universe's own code. But what if that breakdown isn't an end, but a transition? What if the universe has a built-in patch, a cosmic debug, that prevents the ultimate crash? This is where the elegant, mind-bending world of quantum gravity enters the scene. You see, general relativity, while brilliant for describing the vast cosmos, struggles at the incredibly tiny scales. The quantum realm, where particles behave in bizarre, probabilistic ways. To truly understand what happens at the heart of a black hole, we need a theory that unifies these two giants. Among the most compelling candidates for such a theory is loop quantum gravity, or LQG, pioneered by brilliant minds like Carlo Rovelli. LQG suggests something truly revolutionary. It posits that space-time itself isn't a smooth, continuous fabric, but rather a granular atomic structure woven from tiny, discrete loops. Think of it like a piece of cloth that looks smooth from a distance, but up close, you see it's made of individual threads. These quantum threads of space-time have a minimum size, which means that nothing can be compressed to an infinitely small point. This fundamental idea changes everything. If space-time itself is quantized, then there's a limit to how dense matter can become. Instead of collapsing to an infinite singularity, the matter falling into a black hole reaches an incredibly dense state and experiences something extraordinary. A quantum bounce. Imagine a cosmic pressure cooker. A star collapses, its immense mass compressing inward. In the classical picture of general relativity, this pressure cooker has no safety valve. It just keeps crushing. But in the quantum realm, LQG provides that safety valve. As the matter reaches that ultimate finite density, the quantum nature of space-time itself generates a repulsive force. It's a force so powerful that it prevents further collapse, pushing back against the crushing gravity. Instead of an infinite crunch, there's an immediate, violent rebound. A bounce. This quantum bounce is the ultimate escape act. For an external observer, due to the extreme time dilation around a black hole, this process would appear to take an unfathomable amount of time. But from the perspective of the matter inside, the bounce could be almost instantaneous. And what emerges from this bounce? A white hole. This is the breathtaking aha moment that reframes our understanding. The matter and energy that fell into the black hole, trapped and seemingly lost forever, are not destroyed. They are simply held in a hyper-compressed state until the quantum forces overcome gravity, triggering an explosive ejection into another region of space-time. It's the universe's greatest magic trick, a cosmic vanishing act, followed by an equally cosmic reappearance. This transformation also offers a stunning solution to one of the most profound puzzles in theoretical physics, Stephen Hawking's information paradox. You see, Hawking theorized that black holes slowly evaporate over eons through a process called Hawking radiation. But if a black hole completely evaporates, what happens to all the information about the matter that fell in? Quantum mechanics dictates that information can never truly be destroyed. Yet, if a black hole simply vanishes, that fundamental principle is violated. But if a black hole can transform into a white hole, the paradox dissolves. The information isn't destroyed. It's simply stored, encoded, in the compressed quantum foam at the black hole's heart, only to be released back into the universe during the quantum bounce. The black hole becomes a cosmic recycling plant, not a destroyer of information. It's a journey of transformation, a great escape where information isn't lost, but reemerges, perhaps in a completely different form, but fundamentally preserved. If a white hole is the time-reversed solution, its defining characteristic is that nothing can enter its event horizon from the outside. Instead, matter and energy burst forth from within. It's an erupting fountain of creation, continuously spewing out everything it once held captive. However, white holes are also theorized to be incredibly unstable. Any incoming matter, even a single photon attempting to cross the event horizon, could theoretically cause a catastrophic collapse, turning the white hole back into a black hole. Now let's take this astonishing concept even further. We've always seen the Big Bang as the ultimate moment of creation. But what if our universe wasn't a beginning, but an exit? The chaotic, fiery birth of our cosmos could be the other side of a black hole from a universe that came before. This isn't just wild speculation. It's a profound philosophical provocation, grounded in mathematical possibility. The idea of a big bounce suggests that our universe didn't emerge from nothingness, but from the collapse of a previous universe, which then rebounded into ours. Some cosmologists even propose that our observable universe might be the interior of a black hole. This black hole cosmology notes a fascinating coincidence. The Hubble radius of our universe is remarkably close to its Schwarzschild radius, the size of a black hole with its mass. There are even tantalizing, albeit highly speculative, hints in observational data. Consider the mysterious gamma-ray burst (RB 0606-4). observed in 2006. It was unusual, a long-duration burst, without the expected corresponding supernova. Some astronomers speculated it could have been the signature of a white hole's explosive birth. More recently, a 2025 analysis of over 200 early galaxies by the James Webb Space Telescope revealed a potential anomaly, about two-thirds spin clockwise. One speculative explanation is that our universe resides inside a rotating black hole, which would impart such a bias. These ideas challenge us to rethink everything. The human drama of scientific inquiry, led by brilliant minds like Einstein, Hawking, Rovelli, and Novikov, is a testament to our insatiable quest for knowledge, pushing the boundaries of what is conceivable. It's a story of cosmic cycles, where death leads to rebirth, where the ultimate collapse gives way to a new explosive creation. We are perhaps living in the echo of another universe's demise, a universe that, through its own black holes and quantum bounces, birthed ours. The quantum bounce, then, is more than just a theoretical solution. It transforms the black hole from an inescapable void into a cosmic chrysalis, a transformative crucible where the universe recycles itself and where new universes might even be born. The secret back doors to creation may be closer than we ever imagined. Imagine, if you will, the birth of our universe. What comes to mind? A colossal explosion, perhaps, a moment of unimaginable heat and density, expanding from an infinitely small point. This is the Big Bang, our cosmic origin story, a narrative ingrained in our scientific understanding. But what if that story, as grand as it is incomplete? What if the Big Bang wasn't a beginning from nothing, but an exit? This is the audacious, awe-inspiring thesis at the heart of our journey today. That our Big Bang was not a singular, uncaused eruption, but rather the explosive burst of a white hole. Think of our universe as a magnificent firework, brilliantly erupting in a chaotic, fiery display. The conventional view suggests this firework was lit from an unknowable void, but the white hole theory offers a different narrative. It suggests our universe's fireworks was launched from a hidden cannon, a black hole in a parent universe. This concept immediately grabs your attention, doesn't it? It takes a familiar, albeit mysterious, concept, like black holes, and introduces their enigmatic counterpart, white holes. While black holes are cosmic devourers, white holes are their theoretical opposite. This isn't mere science fiction. It's a profound mathematical possibility, born from the very equations that predict black holes themselves. White holes are valid mathematical solutions to Albert Einstein's field equations of general relativity. Indeed, physicists describe a white hole as a black hole's time reversal, like watching a video of a black hole played backward. Where a black hole's event horizon is a point of no return, a white hole's event horizon is a boundary of no admission. Now, for the aha moment, the hot, dense, chaotic state of our early universe, the very conditions we attribute to the Big Bang, are precisely what physicists would expect from matter and energy being violently ejected from a white hole. You stand at the precipice of a staggering idea, a notion so profound, it redefines our very understanding of creation itself. We've whispered about the universe's secret back doors, about the possibility that our own chaotic, fiery birth wasn't a beginning, but an exit, a magnificent, cataclysmic escape from a universe that came before. It's a thought that hums with the electric current of cosmic wonder, challenging everything we thought we knew. But now, a deep breath. Because the truth, the raw, unvarnished truth, is this. For all their breathtaking theoretical elegance, for all their profound implications, white holes remain, for now, a phantom. We have zero direct, undeniable proof of their existence. Not a single telescope, not a single gravitational wave detector has ever definitively pointed to one and said, "There, that is a white hole." This is the critical weakness in our thrilling narrative, the elephant in the cosmic room. So, if white holes are such valid, even beautiful mathematical solutions to Einstein's field equations, the very same equations that predict the black holes we now observe, why haven't we found them? Why do they remain elusive, mere ghosts in the machine of space-time? The answer lies in their inherent nature, a paradox wrapped in an enigma. If a black hole is a cosmic maw that swallows everything, a point of no return from which nothing, not even light, can escape, then a white hole is its direct temporal opposite. Its event horizon is a boundary of no admission. Nothing can enter a white hole from the outside. Imagine that for a moment. You can't fall in. You can't drop a probe into it. You can't even shine a laser beam at it and expect it to be absorbed. Instead, theory suggests that matter and energy erupt out of it. This makes them incredibly difficult to observe directly, because their very definition dictates that we can only see what comes out, not what goes in. And what comes out, according to the mathematics, would be a sudden, violent explosion of matter and light, a cosmic geyser of creation. This brings us to their extreme theoretical instability. Think of a white hole as a delicate bubble, suspended in the fabric of space-time, constantly pushing outwards. The theory suggests that even the slightest disturbance, a single photon attempting to cross that boundary, a stray particle of dust, even a passing gravitational ripple, could cause this fantastical object to collapse back into a black hole. It's as if the universe itself struggles to maintain these bizarre, eruptive entities. They are not stable, enduring structures like their black hole counterparts. They are, instead, fleeting cataclysmic events, moments of explosive creation that might vanish almost as quickly as they appear. Hunting for a white hole, then, is like being a cosmic storm chaser, trying to photograph a bolt of lightning. You're not looking for a stable, permanent feature on the landscape of the cosmos. You're searching for a singular, instantaneous flash, a moment of immense power that erupts and then is gone. You have to be looking at the right place at the exact right time, with the right instruments, and even then, you might misinterpret the flash, mistaking it for something more familiar, something less revolutionary. The universe is vast, and such fleeting moments are easily lost in its grand, sprawling chaos. Yet despite this profound challenge, the concept of white holes isn't mere science fiction fantasy. It's deeply rooted in the very bedrock of our understanding of gravity. White holes emerged as a theoretical possibility from Carl Schwarzschild's 1916 solution to Albert Einstein's general theory of relativity equations, the same solutions that first described black holes. In the 1930s, physicists like J. Robert Oppenheimer and Hartland Snyder explored their implications. It wasn't until 1964 that the Soviet cosmologist Igor Novikov formally coined the term white hole, proposing their possible existence as the time-reversed counterpart to black holes. Mathematician Martin David Kruskal, in 1960, even developed space-time diagrams that clearly showed the mathematical existence of a white hole as part of the eternal black hole solution, a symmetrical partner to the black hole. So the math is there. The equations permit them. But how would they even form? This is where modern theoretical physics steps in, offering a bridge from the purely abstract to the potentially physical. One of the most compelling ideas comes from the realm of quantum gravity, particularly theories like loop quantum gravity, championed by physicists like Carlo Rovelli. This theory suggests that a black hole doesn't truly collapse. into an infinitely dense singularity, that impossible point where our current laws of physics break down. Instead, at the unimaginably extreme densities within a black hole's core, quantum effects kick in, creating a repulsive force that prevents infinite collapse. This phenomenon is called a quantum bounce. Instead of collapsing forever, the matter reaches a maximum density, and then, in an astonishing act of cosmic rebound, it bounces back, expanding outwards. And what does this outward expansion look like? An eruption of matter and energy. From the outside, what was once a black hole, having consumed and compacted everything, transitions into a white hole, ejecting all that it once consumed. This quantum bounce theory offers a stunning resolution to one of the most profound puzzles in modern physics: Stephen Hawking's black hole information paradox. For decades, physicists have wrestled with the problem of what happens to the information of everything that falls into a black hole. Does it vanish forever, violating a fundamental principle of quantum mechanics that information can never truly be destroyed? If a black hole can transition into a white hole through a quantum bounce, then the information isn't lost. It's simply stored, processed, and eventually released back into the universe. It's a cosmic great escape, reframing the paradox not as a problem of loss, but as a journey of transformation. The black hole is not a cosmic shredder, but a kind of cosmic chrysalis, incubating matter and information before its spectacular rebirth. From an external observer's perspective, before this eruption, a white hole might look indistinguishable from a black hole. They would both possess mass, could have charge and angular momentum, and would exert gravitational pull on nearby objects. The critical difference would only become apparent when the white hole, in its unstable glory, began its explosive outpouring. It's like looking at two identical doors. One leads to an abyss, the other to a new, brightly lit room. But you only know which is which when one of them bursts open, given their instability and fleeting nature. How could we possibly hope to detect these cosmic lightning bolts? This is where the detective work begins, where cosmologists become cosmic storm chasers, sifting through the universe's most violent and mysterious events for the faint, anomalous fingerprints of a white hole. We might not see the white hole itself, but we might see the aftermath of its birth. This brings us to a tantalizing unsolved case that has perplexed astronomers for years: the gamma-ray burst GRB-X0614. Gamma-ray bursts are the most powerful explosions in the universe, typically associated with the collapse of massive stars into black holes, long-duration GRBs, or the merger of neutron stars, short-duration GRBs. They are incredibly bright, brief flashes of high-energy radiation, like cosmic fireworks, signaling a star's dramatic demise. GRB's 060614, observed on June 14, 2006, was an anomaly. It was a long-duration gamma-ray burst, lasting for over 100 seconds. Usually, such an event would be followed by a supernova, the bright, expanding cloud of debris from the exploding star. But GRB's 060614 had no supernova, none. It was a powerful, prolonged burst of gamma rays, but the star it supposedly came from simply vanished, without the expected fiery aftermath. It was a cosmic flash without a corresponding bang, a death without a corpse. This unusual property left astronomers scratching their heads. What could produce such an intense, long-duration burst without the telltale sign of a stellar collapse? Some astronomers, with a speculative twinkle in their eyes, suggested a radical possibility. GRB-X0614 could have been the signature of a white hole's emergence. Imagine a primordial black hole, perhaps formed in the very early universe, having quietly undergone its quantum bounce, finally erupting into a white hole. That eruption would release an immense amount of energy, precisely the kind of energy we see in a gamma-ray burst, but without the need for a dying star and its subsequent supernova. It was a flash in the cosmic darkness, an event that defied easy categorization, and for some, it was the closest thing we had to a phantom's fingerprint. Beyond GRB 060614, the search continues. Physicists like Carlo Rovelli proposed that primordial black holes, those tiny ancient black holes formed in the universe's infancy, might be the most likely candidates for this quantum bounce transition. Their explosive deaths as white holes could manifest as other high-energy cosmic events, perhaps even the mysterious fast radio bursts, FRBOs, that pepper our skies, incredibly powerful, extremely brief radio pulses from distant galaxies whose origins are still largely unknown. The Big Bounce theory, an alternative to the Big Bang, also finds resonance here. In this model, our universe isn't born from an infinite singularity, but emerges from the collapse of a previous universe, undergoing a bounce and re-expanding. This Big Bounce could, in essence, be described as a white hole event, where our entire universe emerges from the other side of a previously collapsed cosmos. Even more provocatively, some cosmologists have proposed that our observable universe might actually be the interior of a black hole existing in a larger parent universe. This black hole cosmology notes a peculiar coincidence. The Hubble radius of our universe, the edge of the observable universe, is remarkably close to its Schwarzschild radius, a key characteristic of black holes. And if our universe is inside a black hole, then our entry point, our Big Bang, could be seen as the white hole through which we emerged. Consider the recent 2025 analysis of early galaxies by the James Webb Space Telescope, which found that about 2/3 of over 200 observed galaxies spin clockwise. While there are many possible explanations, one speculative idea suggests that if our universe resides inside a rotating black hole, that rotation could impart a preferred axis of spin to everything within it. It's a subtle bias, a cosmic leaning that might hint at a grander, stranger structure for our entire reality. So, while direct evidence remains elusive, the universe is constantly whispering its secrets, leaving behind faint, anomalous clues. The hunt for white holes is a testament to the human spirit of inquiry, a relentless pursuit of the extraordinary within the ordinary. It's about looking at the unsolved cases on the desks of cosmologists, the events that defy conventional explanation, and daring to ask, could that be it? Could that anomaly be the very fingerprint of a white hole we've been looking for? A fleeting glimpse of creation's most magnificent and unstable exit. The universe, in its boundless mystery, continues to invite us to keep looking, keep questioning, and keep dreaming of what lies just beyond the veil of our current understanding. For so long, we've looked at the Big Bang as the singular, explosive genesis of everything, a moment of creation from absolute nothingness. But what if that perspective is incomplete? What if the universe's beginning wasn't a beginning at all, but an exit, a profound opening from a cosmos that came before? This is where the mesmerizing, mind-bending idea of white holes truly takes hold of our imagination. Imagine, if you will, the profound mathematical elegance of Albert Einstein's general theory of relativity. It's a tapestry of space-time, gravity, and the very fabric of reality. Within this tapestry, Carl Schwarzschild, in 1916, found an exact solution that described a non-rotating, uncharged black hole. But here's the astonishing part. Embedded within those same equations, a direct temporal opposite emerged. If a black hole is a one-way street, where nothing, not even light, can escape once it crosses the event horizon, Then its mathematical inverse, the white hole, presents a boundary of no admission. Nothing can enter a white hole from the outside. Instead, these theoretical objects are predicted to erupt, spewing forth matter and energy, a cosmic geyser in reverse. Igor Novikov, a Soviet cosmologist, formally proposed their possible existence and coined the term white hole in 1964, imagining them as the time-reversed counterpart to black holes. Think about that for a moment. If you could rewind the cosmic movie of a black hole, playing its collapse and consumption in reverse, what would you see? You'd witness an explosion, matter and energy erupting from a central point, forever pushing outwards. That, in essence, is the conceptual vision of a white hole. Mathematicians like Martin David Kruskal in the 1960s even developed space-time diagrams known as Kruskal-Shekharez coordinates that beautifully illustrate the mathematical existence of a white hole as an integral part of an eternal black hole solution. Yet, the universe we observe is filled with black holes, and we have zero direct observational evidence for white holes. This apparent absence begs a crucial question. If they are mathematically valid, why don't we see them? The answer, many physicists believe, lies in their inherent instability. Theory suggests that even a single photon, attempting to enter a white hole, could cause it to catastrophically collapse, instantly turning it back into a black hole. This fragility means they couldn't exist for long in our universe without quickly reverting to their more stable, consuming counterparts. They are, by their very nature, a fleeting, explosive moment. But what if their fleeting nature is precisely the point? What if their existence isn't meant to be prolonged, but rather represents a pivotal, almost instantaneous transition? This brings us to one of the most compelling and cutting-edge theories surrounding white holes, the quantum bounce.